This is the first of 2 lectures on polarity, and we're going to use this in order to determine if a molecule is polar or nonpolar. But first we need to be able to figure out whether a bond, a single bond within a molecule, is polar or nonpolar. So as part of this lecture, we're going to review the difference between ionic and covalent bonds, because covalent bonds are the only ones that are polar and nonpolar. We're going to identify and explain the trend in electronegativity, which is what determines polarity. And we're going to use a term I call Funkelbrich to be able to compare 2 atoms that are not in the same period or the same group in terms. So first of all, let's do a quick review of ionic and covalent bonds. An ionic bond is when you have an electrostatic attraction between 2 ions, which has happened after electrons have been transferred, meaning one atom has given its electrons away to the other atom. Now one of them has a positive charge and the other has a negative charge, and as a review, just based on Coulomb's law, the positives and negatives we know opposites attract. We're going to talk about covalent bonds in this unit, because in a covalent bond the electrons are not permanently transformed, they are going to be shared. And when you share electrons, that sharing can be evenly done or unevenly done, and that's what determines whether it is a polar covalent bond or a nonpolar covalent bond. So it is important to remember the difference. When looking at a molecule, you can also determine whether the bonds are ionic, because you will generally have a metal and a nonmetal, and covalent bonds are always formed between 2 nonmetals. So if you look at the elements that are making up the bonds, then you can determine whether it's ionic or covalent. So what determines polarity and what makes the bonds be evenly or unevenly shared is this idea of electronegativity. It's electronegativity, not electronegativity. So what this is the amount of pull that one atom exerts on the electrons it is sharing with another atom, or how attractive one atom is to the electrons. So for example, we have a tug of war going on here between 2 elements. The rope represents any shared electrons. So I'm going to draw 2 dots here as if this was a Lewis dot structure between nitrogen and fluorine. And in this example, nitrogen is less electronegative than fluorine. And what this means is that these shared electrons are going to be spending more time with the fluorine. They're going to be attracted to the fluorine more than the nitrogen. So let's look at why this is. The trend in electronegativity in a period is that it increases from left to right across a period. The reasoning for this is very similar to what we learned earlier in the year with the trends for atomic radius and for ionization energy. All elements in the same period have the same amount of electron shielding. We already know this because they have the same number of energy levels. But elements in the same period have different nuclear charges. And to review that, the nuclear charge is based on the number of protons. So therefore, the element with the stronger nuclear charge, in other words, more protons than the other element, is going to be more attractive to the bonding electrons. And what that means is it's going to be more electronegative than the element with the weaker nuclear charge. And this should make sense because electrons are negative, protons are positive. And so if you have one side of a bond that has a very strong positive charge because it has a greater or stronger nuclear charge, the electrons are going to be pulled towards it, just like any other case where you have opposite charges attracting. Again, the trend going down within a group is very similar to that we learned earlier in the year. All elements in the same group have the same amount of nuclear charge. This is because they have the same amount of valence electrons. But they are going to have different electron shielding. They're going to have different numbers of energy levels. So some will have thicker electron shields with lots of energy levels, some will have thinner. The deal is here, the element with the thinner or weaker electron shielding, meaning it has less energy levels, is going to be more attractive to the bonding electrons, more electronegative. And this means it is more electronegative than the element with the thicker electron shielding. So elements with when you're comparing two elements in the same group, the one with less electron shielding is going to attract the bonding electrons more. So as we said earlier, ionic bonds do not involve polarity because they don't share electrons. So polarity, you're never going to talk about a polar or nonpolar ionic bond. You are only going to refer to this with covalent bonds. So let's first talk about what it means to be a nonpolar covalent bond. Nonpolar means that there is not a north pole or a south pole, or that there is not a positive pole or a negative pole. The reason there is not a positive side or a negative side or polarity to this bond, for example in N2, where this would be nitrogen and another nitrogen, is because the electrons are equally attracted to both atoms. So they're not going to be more on one side than the other. This only happens when the atoms are equally electronegative, which means that they're the same atom pretty much. So any diatomic molecule such as N2, H2, F2, O2 are going to be nonpolar. Now if you have two different nonmetals, now you're going to have a polar covalent bond because electrons are going to be unequally attracted to the atom. So in this example you have nitrogen and fluorine, which we saw earlier, and we already knew that fluorine was more electronegative. Well, we know the reason now is if we compare them, these two elements are in the same period, so they have the same amount of energy levels, which means they have the same amount of electron shielding. However, fluorine has a stronger nuclear charge than nitrogen because fluorine has more protons. So it is going to be able to pull more strongly on the shared electrons. So that is why it is shown as the bigger, stronger person pulling the rope here. So to summarize, the more electronegative atom, when you're comparing the two atoms, the one that is more electronegative is more attractive to the bonding electrons. And that means it's going to have a relatively negative charge. And we use this symbol. This looks like a lowercase g. It's actually a lowercase Greek delta for delta positive and delta negative, meaning partially negative or relatively negative compared to the other atom. So the more electronegative atom will have a relatively negative charge because the electrons are closer to it. So we can't write that it is going to have an absolute negative charge because it is not an ion. The electrons are still shared. They don't belong to that other atom. So we only can say that it is relatively negative. That's why we use this symbol as opposed to saying -1 or -2 like we would for ions. In contrast, the other atom, the less electronegative atom, will have a relatively positive charge, which we denote with the delta positive, because the bonding electrons are farther from it. And so this is similar to the electrons going over to the more electronegative atom, and now it has extra electrons compared to protons, so it's negative. And the other one is going to be left being partially positive because the electrons have left it, and so it has relatively less electrons than protons. So this is similar to ionization, but it's only part of the way. That's why we say it's partially negative or relatively negative. So again, back to our nitrogen and fluorine, we would label nitrogen as being the partially or relatively positive of these two, and fluorine is the relatively negative of the two. And again, this is because fluorine is more attractive to the electrons it's sharing. Nitrogen is the positive because the electrons are leaving it to be closer to the more electronegative fluorine. So electrons are traveling in this direction from the nitrogen to the fluorine. So in addition to knowing the trends across and down, we can also use this term Funkelbrich to determine the relative electronegativity of two atoms when we're talking about the 9 most commonly used nonmetals. So Funkelbrich, as you can see, is fluorine, oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, hydrogen. The atoms in the front, fluorine being the more electronegative side of the Funkelbrich term, and the ones in the back, hydrogen, is the least electronegative out of all of these. So we can use Funkelbrich as a sort of a cheat shortcut to figure out whether with two atoms in a bond, which is the more partially or relatively negative and which is the more relatively positive. So using Funkelbrich, if we looked at, instead of the same example we've been using, let's look at instead nitrogen and iodine. We can tell that nitrogen in this case is the more electronegative atom, and so we drew it bigger, and that's because it comes before I in Funkelbrich. Now, if we compare these two on the periodic table, nitrogen and iodine are in different groups and different periods, so we wouldn't normally be able to use the rules of the trends, but by using Funkelbrich, we can tell that nitrogen is going to be the more electronegative. Therefore, it's going to have the partially negative symbol, and it's going to be pulling the electrons closer to it compared to the iodine. So there's a few examples here that you can look at, one of which is HF and F2. So I want to show you a picture of what these two look like really quick. Here I'm going to show you a simulation that you're able to look at if you want to. It's from this website, PHET, from the University of Colorado. And in this simulation we have here the actual values of the electronegativities for hydrogen and fluorine, hydrogen being 2.1 and fluorine being 4.0. Those are the you don't have to memorize those are just the numbers. So we already know by looking at these numbers that fluorine is the more electronegative. But if we put in the partial charges, the difference between the two make it that this one is going to be the partially negative and this is the partially positive, the hydrogen. And so if we wanted to see which way electrons were moving, we can put in this arrow that shows the bond dipole, and it shows that they're moving in the direction from hydrogen to fluorine. In our next unit, in our next lecture, we're going to be using this arrow a lot to show the polarity of a molecule. And if we want to, we can add the electron density in, and it's going to show that the electrons are less dense around the hydrogen and more dense around the fluorine, which is why the fluorine is going to have that partially negative or relatively negative charge compared to the hydrogen. So if we look at two atoms, and let's say that again this is the hydrogen and the fluorine is much more electronegative than the hydrogen, this is how they are going to look in electric or magnetic field. They're going to orient so that the negative side is going to align with the positive side of the field. Next week, in our next unit, we're going to look at how that's affected when you have three different ones, such as if we have water where this is going to be the oxygen is the more electronegative, and A and C are both hydrogen. If we turn the electron field on, the electric field, we see that it rotates so that it lines up where the positives are going to be aligned with the negative side and the negative is going to be aligned with the positive side. The other example was two fluorines, and that looks like this. So with the two fluorines, we know that this is going to be a nonpolar because we can see that their electronegativity value is 4, and so obviously they're both the same. And so the electron density is equal among both. There is no arrow. We couldn't draw an arrow because there is not one side that is more positive than the other. So in a electron field or in a magnetic field, it's not going to orient in any particular way because there is not a positive side or a negative side. So we just looked at these two. You can go ahead for practice to fill in the type of bond, meaning is it ionic or covalent? Polarity, meaning is it polar or nonpolar, or does it not apply? And then why? And then you can go in and check your answers here. And we already looked at these two again, so we already knew that those were polar and nonpolar. And again, the reason is because the difference between F and H and their electronegativity values, and here with F2, they're the same, so there is no difference in electronegativity value. Good luck!